Greetings everyone, this is Mr. Mull, and in this podcast I'm going to be going over our final lesson. But first off, I want to get you kind of warmed up. So try to pause this podcast and try to figure out which one of the following objects qualify as being in static equilibrium. And the forces shown are the only forces acting on the objects. The dot simply shows the center of each object. So pause this and take a moment to see what you come up with. Alright, welcome back. So, in order for us to determine if an object is truly at static equilibrium, a complete state of lack of motion, we need to have both not only the net force be zero, but also the net torque be zero. So only if both conditions are met will we have an object in static equilibrium. So look at the first one here, and it looks like I've got a net force definitely to the left. So this object here is definitely not going to be in static equilibrium because the net force is not equal zero. I've got two forces to the right and nothing balancing to the left. The second object, it looks like we've got equal and opposite forces, so the net force is zero. But this force is applying this object is free to rotate. This object is going to be able to rotate it that way, and so is this one. So if there's my axis in the center, this one is going to apply a torque, and so the net torque is not equal zero. We've got two torques in the clockwise direction. Last but not least, we have this object here. So when I look at the forces, excuse me, we've got two forces to the right, and they are totaling 150 newtons, and 150 newtons going to the left. So the net force is zero. Let's see if the net torque is zero. So I'm going to go ahead and look at this here. I'm just going to call this little guy here R, and it looks like here is 2R. And so if I look at this here, if I make the center my axis, that 150 newtons isn't going to torque at all. So clockwise, we've got 50 newtons at 2R, and then we've got 100 newtons at R, and they are in opposite direction. So this is clockwise, this is CCW, and of course those are going to cancel with each other, meaning that the net torque is also zero. So only this object is going to be in static equilibrium. The other two objects are not going to be. So this one was in static equilibrium because both net torque and net force is zero. Alright, let's go ahead and do our final lesson with some harder static equilibrium problems. And so if you need to watch this a couple times to get a handle for it, I recommend it. Especially the sign question. You really want to make sure you get a handle on this one. Alright, so bear with me for a second. Alright, so this is example number 29 in your handout. And turns out there's actually a lot of physics involved in a sign that's hanging. So here's a I love static equilibrium sign that's hanging, and so a couple things going on here. There's a hinge here that is keeping it from sliding up and down the wall, and then on the other end is a rope or a string that's tied to back at the wall and is supporting it. So we've got this rectangular sign. It's 4 meters wide, and it's suspended from a horizontal 5 meter long rod, so that the sign's right edge is lined up with the rod's right end. The weight of the rod is 80 newtons, and the left end of the rod is supported by a hinge. The right end is supported by a thin cable making a 20-degree angle with the horizontal, as shown in the picture. Find the tension in the cable. Okay, that's going to be over here in this cable, and the horizontal and vertical components of the force exerted on the left end of the rod by the hinge. So the hinge is pushing back on the rod and is keeping the rod in the sign from falling. So we're looking for the horizontal and vertical components, and then if we had to, we could take the result and find the actual force of the hinge if I wanted to. I'm also looking for the overall tension force in the rod. So I'm going to draw a little bit bigger picture of my sign here. So here's my hinge, and I'm going to go ahead and draw my sign. Okay, there it is, and I'm going to draw a couple different things on it. So I've got my at the edge of this thing here. Okay, I got my, sorry, that's not a very straight line. Here's my force of tension, and that's going to be at 20-degree angle. Okay, and I can think of that force of tension as being, it's at an angle. So usually when I have forces at angles, I need to break them into components. So I'm going to do that. So I've got my, I've got my force of tension here. I can think of it as being an x component and a y component, pulling to the left and up on that sign. And then we've got, it says that the weight of the rod is 80 newtons, so I'll draw a little 80 newton force going down there in the center of the rod. Okay, so I'll say that's 80 newtons. That's the force of gravity on there. And then that's in the center of the rod, so I can go ahead and draw here that that is at 2.5 meters because it was a 5-meter rod. Okay, some other ideas. It says we've got the hinge, and then it looks like there is a sign that is suspended from the rod. So this sign is pulling down on the rod, and that sign is going to be suspended so that the sign's right edge goes all the way to the end of the thing, and then that sign itself is 4 meters. So I'm just kind of drawing out some things here. So this says it was 4 meters. Okay, and because the sign is at 4 meters, then halfway through the sign is going to be 2 meters. Okay, 2 meters. And because the sign is at the edge of the bar, that sign is going to be pulling down. So the center of the sign is going to be where I'm going to treat as if the sign was pulling down on the rod at 2 meters. So I've got these two little things here. I'm going to assume the sign is pulling equally. I'm going to treat it center of mass so that in effect the sign is pulling down at the center of the sign, which was 2 meters away, and that sign was 300 newtons. Okay, so 2 meters from the edge of this edge here, and that's actually going to be, because the sign is 5 meters, 3 meters from the hinge. Okay, 2 meters from the edge. I'm going to go ahead and draw that 300 newton sign pulling on the rod. Okay, the center of the sign pulling down. So I need to have set in static equilibrium. So I need to have all the forces that are acting on the rod, and I put that in terms of the let's see, we've got this force of the hinge going on here. So the hinge is pushing out. Okay, we'll call that FHX. Okay, it's pushing back on the rod's pushing on the side of the wall, and the hinge is having to push back, and then the rod is pulling down on the hinge, and so the hinge is pushing back up on the rod. Okay, so we'll call this FHY. Okay, so there's a lot going on here. So the reason why I need all these forces is because net torque equals 0, net force is equal to 0, and I need everything in terms of components so I can figure out forces up, forces down, forces left, forces right, and then anything that's causing a torque. So I'm going to make the axes the hinge, because right now I don't have FHY or FHX. I don't have anything there. So I'm going to make that the axes right now, and that's going to allow me to work on this tension force first out there, FT. So I'm going to do that. I'm going to work on that tension force, and I'm going to make the axes so that I can look at torques. Okay, so the clockwise torque and the counterclockwise torques are going to be equal. And so clockwise we have the 80 newtons. Okay, so remember, to calculate the torque, I can do RF sine of theta, or I can do R perpendicular F. Okay, or one that I haven't used a whole lot is R F perpendicular. Okay, I haven't used that one a whole lot, but the book mentions it, and I also used it way earlier. I could also use that too if I needed to. Okay, so let's go ahead and go back to calculating. So clockwise, we have the 80 Newton force, and it's right at the center of the rod, and so that's going to be at 2.5 meters. Okay, and then I've got that plus, I've got that 300 Newton torque from the sine, and it's essentially acting out at 3 meters from my hinge. And then counterclockwise, I have just the tension, but only the y component of the tension. Okay, so I'm going to call this FTY, and that y component of tension is acting out at the very edge of the rod, and that's going to be at 5 meters. So when I solve for FTY, I'm going to get that the y component of tension is 220 newtons. 220 newtons. Okay? So I want to find that overall tension. Thankfully, I know the angle already. So I can actually use an angle and some trig to find that force of tension, the hypotenuse. So I'll use sine. So 20 degrees is going to be equal to opposite over hypotenuse. So that opposite was, my opposite was FTY, 220, over the hypotenuse was FT, and so I can solve for my force of tension as being 643 newtons. Okay. Don't forget that to get FT by itself, I would of course have to cross multiply and get FT to the numerator and then solve out. Okay, so I actually found the force of tension. Done. I didn't need to use any forces up, forces down. I was able to use just my my torque ideas. So now I want to come back and find forces in the hinge. Okay, so what I'm going to do is I'm going to use the fact that it's in static equilibrium to evaluate the forces. I know Ft and I know Fty. So this was 643 newtons. So what I'm going to do now is I'm going to use my forces up equal forces down idea to try to find the other thing here. Because I know the force of tension is the only leftward force, at least the Ftx is, I can find Fhx by using my forces right equal forces left. So going to the right, I've got my force Hx, which is what I'm solving for. Force to the left is Ftx, okay, which using my hypotenuse, which I now know, 643 cosine of 20 degrees, I can solve for Ftx, and it's going to be 604 newtons. Okay, that's what I wanted to solve for, 604 newtons. Okay, to find the Fty, I can do forces up equal forces down. So I've got two forces up. I've got Fhy plus also going up was Fty, which we saw for a second ago was 220, equal my downward forces, which were 380. Okay, add those together. I can solve for my force Hy is equal to 160 newtons. Okay, so I was able to find all the forces components in the hinge. Now, if I were to ask you, let's say on a quiz or something, to find the overall force in the hinge or the resultant force in the hinge, then of course you would have to put the vectors back together and find the actual force of the hinge by using Pythagorean theorem. Now that I know that the y component is 160, the x component is 604, and I could go and solve for that. Okay, so make sure that you could do that. The last example problem is one where I have an object kind of like hanging. So this is like a steel rod, and it's placed in the corner between the floor and a wall, and it's balanced at an angle using a cord that's attached to the wall. And the rod is balanced such that the top end is 2.38 meters from the wall. Okay, 2.38 meters from the wall. And then it says the cord is 40 centimeters long. 0.40 meters. And it's attached to the wall at a height of 75 centimeters above the ground. Okay, so this is 0.75 meters. The diagram shows the situation. If the lower end of the rod does not slip from the corner, what is the tension in the cord? Okay, so I'm trying to solve for this force of tension. So I'm just going to kind of draw this into a little force here acting. And I want to find this force of tension in the cord. Okay, so if that's the force of tension acting on the rod, I'm going to treat it as a uniformly distributed mass, and I'm going to also draw a force of gravity acting on the rod right at its center. Okay, there's a force of gravity acting at its center, and I'm going to try to figure out what that tension is. So what I'm going to do is I'm going to notice in static equilibrium, so net torque is 0 and forces up equal forces down. And so this object looks like it's not rotating. I'm going to try to approach it from a torque situation because I've got these forces which looks like they could be, I've just got two forces, and I'm going to make the axes down here because I know enough information about those other forces, distances, where they're at. I'm going to try to figure out what the torque clockwise and torque counterclockwise is. Okay, so torque clockwise equals torque counterclockwise, and clockwise, I've got that force of tension acting, and it's going to be acting at the radius perpendicular. So there's my force, and I'm going to go ahead and draw my little radial line here. It's going through that force. Okay. So in order to find torque, remember, we recall, is going to be R perpendicular F or R F perpendicular. Okay. So I'm going to use this one here, R perpendicular F, and what that means is it's the component of the radius that's perpendicular to the direction of F, perpendicular to direction of the force. So I have my R here. This is R going out to there. The perpendicular component of that is just going to be perpendicular component to that force. It's going to be 0.75 meters. Okay, so my radius goes all the way out there. The perpendicular component to that force is going to be 0.75 meters. So I'm going to put on here Ft times 0.75 meters, and that's equal to, then the counterclockwise torque is going to be just the force of gravity, and so Rg perpendicular. So when I look at the radial line going out to here, what is the component of the radius? So here's the R here, that's perpendicular to that force. Okay, that's going to be, see, here's my, it's going to be this little guy here. The component of the radius perpendicular to that force is going to be Rg perpendicular. So there's going to be, notice that I've got my my R perpendicular is going to be from the axes out to where my force of gravity is, and that's going to be the little R perpendicular for the force of gravity. So equals, force of gravity is 2,000 newtons times 1.19 meters. And where do I get 1.19 meters? Well, we're going to assume it's going to be acting in the center of the rod. So 2.38 divided by 2, that was how far the edge of the rod was from the wall. So that's where our center of gravity is going to be. And so when we do this, work it out, force of tension is going to be equal to 3,173 newtons. Okay. So the biggest trick here is trying to figure out where our perpendicular is. To do so, you can just draw a little line in between your line of action where the force is acting and the radius, and you're trying to find the line that's perpendicular to both of those things. Okay. Alright, I hope that this has been helpful, and you'll have 15 minutes before our quiz on the next day to ask questions. Bring them if you need to. Have fun.